How do you build a machine that can dive silently to the bottom of the ocean, withstand crushing pressure, and stay hidden for months? Today, we're diving deep into the incredible world of submarine construction, and then I'll share a story about one submarine that changed history. Let's start with the heart of any submarine, the hull. This isn't just any metal shell. Submarines operate at depths where the water pressure is immense, over 1,000 pounds per square inch in some cases. To survive this, the hull is made from special high-yield steel alloys, sometimes even titanium for the deepest divers. Imagine giant, curved plates of this super strong steel, some several inches thick. These are meticulously welded together to form massive rings or cylinders. The precision required here is mind-boggling. A single weak weld could spell disaster, so every single seam is inspected using X-rays and ultrasonic tests to ensure it's absolutely flawless. It's like a tailor creating a suit of armor, but for a giant of the deep. Once these cylindrical sections are complete, they are joined together to form the long, cigar shape we all recognize. This is the pressure hull, the inner fortress that protects the crew and equipment from the crushing depths. But a submarine is more than just a strong tube. Surrounding this pressure hull is a lighter, outer hull. This outer shell is hydrodynamic, meaning it's shaped to move through the water with minimal resistance and noise. The space between these two hulls is crucial. It houses ballast tanks. By flooding these tanks with water, the submarine becomes heavier and sinks. To surface, compressed air is blown into the tanks, forcing the water out and making the submarine buoyant again. It's a surprisingly elegant dance with physics. Inside the pressure hull, it's a different world. It's a maze of decks, compartments, and a labyrinth of pipes, cables, and ducts. We're talking hundreds of kilometers of wiring and piping, all snaking through the tight confines of the sub. Everything has to be installed in a very specific order, a 3D puzzle of epic proportions. You can't just decide to add a big pipe after the walls are up. The entire construction is planned out using advanced computer-aided design, or CAD, software long before the first piece of steel is even cut. The interior is divided into watertight compartments. This is a critical safety feature. If one compartment floods, sealed doors can prevent the water from spreading to the rest of the vessel, giving the crew a fighting chance to survive and surface. As these compartments are being fitted out, all the major components are lowered in through large openings in the hull. This includes the massive diesel engines, electric motors, generators, and of course, the nuclear reactor for nuclear-powered subs. Speaking of power, let's talk about the engine room. In a conventional diesel-electric submarine, giant diesel engines run on the surface to charge massive batteries. Underwater, the sub runs silently on these batteries using electric motors. The challenge is that they need to surface periodically to run the diesels and recharge, which makes them vulnerable. Nuclear submarines, on the other hand, have a game-changing advantage. A nuclear reactor heats water to create high-pressure steam, which spins turbines that generate electricity and also drive the propeller directly. This gives them virtually unlimited range and endurance. They can stay submerged for months at a time, limited only by the amount of food they can carry for the crew. The process of installing a nuclear reactor is one of the most complex and secretive parts of the entire build, requiring extreme safety protocols. Then there's the brain of the submarine, the command and control center. This is where the captain and the crew operate the vessel. It is packed with an incredible array of technology. So are screens that paint a picture of the underwater world using sound navigation systems, periscopes, which are now often high-tech optronic masts, with cameras instead of traditional lenses, and the fire control systems for launching torpedoes or missiles. All of this sensitive equipment is installed on shock-absorbent mountings to protect it from the violent jolts of underwater explosions. One of the biggest challenges in building a submarine is making it quiet. Silence is survival. Any noise, a clanking pipe, a humming motor, the churn of the propeller can be detected by enemy sonar. To combat this, everything is designed to be as quiet as possible. Engines and machinery are placed on massive rubber mounts called rafts that absorb vibrations. The outer hull is covered in special anechoic tiles, which are rubbery coatings that absorb sound waves rather than reflecting them, making the submarine harder to detect on active sonar. Even the shape of the propeller is a closely guarded secret, designed to move water with minimal cavitation, the formation of noisy bubbles. The final stage of construction is the launch. Unlike a surface ship that slides dramatically down a slipway, submarines are often moved onto a massive floating dry dock or a shiplift. The dry dock is then submerged, and the submarine floats for the very first time. But it's far from ready. This is when a long and intense period of testing and sea trials begins. The sub will perform a series of dives, getting progressively deeper, testing every system, every valve, every weld under real-world pressure. They test for speed, maneuverability, and of course, stealth. Only after passing hundreds of rigorous tests is the submarine commissioned and officially handed over to the Navy. The entire process, from the first still cut to commissioning, can take 5 to 10 years and cost billions of dollars. Now, for that story I promised, it is about a submarine that demonstrated the true power of underwater stealth and endurance. The American nuclear submarine, the USS Nautilus. Launched in 1954, it was the world's first operational nuclear-powered submarine. It completely revolutionized naval warfare, but its most famous mission was Operation Sunshine. In 1958, the Nautilus achieved the impossible. It embarked on a top-secret journey to travel from the Pacific to the Atlantic Ocean, not by going around a continent, but by going under the Arctic ice cap and across the North Pole. Imagine the challenge. For this journey, there would be no surfacing. They would be trapped under a ceiling of ice, sometimes hundreds of feet thick. GPS didn't exist, and magnetic compasses are useless near the pole. They had to rely on new, experimental inertial navigation systems to know where they were. For 96 hours, the 116 crew members of the Nautilus navigated through a treacherous, uncharted underwater world. They were completely cut off from the outside world, alone under the ice. On August 3, 1958, Commander William Anderson announced to his crew, "For the world, our country, and the Navy, the North Pole, they had become the first vessel in history to reach the geographic North Pole." This wasn't just a stunt. The journey of the Nautilus proved that nuclear submarines can operate anywhere on Earth, hidden from view, opening up a new, strategic route between the world's two largest oceans. It was a monumental feat of engineering and human courage, born from the same incredible construction process we've talked about, from carefully welded steel plates to a crew of brave explorers. The story of the Nautilus is a testament to what is possible when we push the boundaries of technology and venture into the unknown. Building a submarine is one of the most complex engineering feats humanity has ever undertaken. It's a combination of raw power, delicate precision, and cutting-edge science. And every single one that sails is a marvel of human ingenuity, a silent guardian of the deep. Thank you so much for joining me on this deep dive today. If you found this fascinating, make sure to hit that like button and subscribe for more stories from the world of incredible engineering. See you next time.